Welcome to Isinamuva Tutoring. This is Peter from Foslorus. In this video, I'll be taking you through the Euclidean Geometry grade 11 and grade 12. Please be sure to subscribe to our channel, like the videos, comment, and share them as well. And be sure to turn on the notification bell so that whenever I post a new video, you get notified. Okay, let me start off by introducing you to triangle theorems, the different types of triangles and the properties of those triangles, because that's fundamental. You can't just go straight to the complicated theorems, your tan chord theorem, your angles in the same segment theorem, your opposite angles of the cyclic chord, without first understanding the basics. So let's consider triangle ABC to be any type of a triangle. So let's say this is triangle ABC. A, B, C. I'm sure we already know that whenever you add angle A, angle B, and angle C, you're gonna get 108. That's the first theorem, and it's true for any type of a triangle. When you say angle A plus angle B plus angle C, you're gonna get 180 degrees. Angles in a triangle, or sum of interior angles of a triangle. So be sure to familiarize yourself with this theorem, because it's so important. We're going to be dealing with triangles throughout the chapter. Now let's look at different types of triangles. We have equilateral triangle. An equilateral triangle, as the name might suggest, is a triangle with equal sides, a triangle with equal angles. So if I have triangle ABC, triangle ABC with side AB equals side AC equals side BC, then I can conclude that this triangle is an equilateral triangle, and therefore angle A equals angle B equals angle C. I'm sure you still remember that angle A plus angle B plus angle C equals 108. So if angle A equals angle B equals angle C, then I can let angle A equals X. So if angle A equals X, then angle B is X and angle C is X as well, equals 180. X plus X plus X is 3X. So 3X equals 180, and then divide by 3 on both sides. I'm going to get X equals 60 degrees. This is true for any equilateral triangle. So with the equilateral triangle, all angles are equal and all angles are 60 degrees. Moving on to an isosceles triangle. An isosceles triangle is a triangle with two equal sides and two equal angles. For example, let's consider again triangle A, B, C with AB and AC being equal. Now, if that's the case, then this triangle is an isosceles triangle. Remember, an isosceles triangle is a triangle with two equal sides. So we have AB equals AC in this triangle. Then the sides or the angles opposite these two equal sides are also equal. An angle opposite side AC is angle B. An angle opposite side AB is angle C. So this is true for an isosceles triangle. You have two equal sides and two equal angles. It doesn't matter how the orientation of the triangle is. For example, let's say you have something like this and this one being equals to this one. You know that these two angles are going to be equal. Say this is ABC. The nice thing about the isosceles triangle is that let's say you are given that angle B is 30 degrees. So if B is 30 degrees, one can conclude that angle C is also 30 degrees. Angle C is also 30 degrees. The reason for that is angles opposite equal sides are equal. So after concluding that angle C is also 30 degrees, then we are able to determine what angle A is. Because angle A plus angle B plus angle C equals 180. Remember, angles in a triangle are supplementary. We are looking for angle A. We already know what angle B is. Angle B is 30 degrees plus angle C is 30 degrees equals 180. So from here we can easily determine what angle A would be. 180 minus the sum of those two known angles, angle B and angle C. That is 180 minus 60 degrees. 180 minus 60 degrees is 120. So angle A is 120 degrees. That's the nice thing about the isosceles triangle. Another thing to remember is that whenever you are given an angle between equal sides, let's say we were given angle A, you are able to determine angle B and angle C at the same time. This is how we're going to determine what angle B and angle C is. We just say angle B equals 180 minus the given angle, the one that is between two equal sides, all over 2. And then you're going to get your 30 degrees. That's your angle B, also equals angle C. This is very important to remember of an isosceles triangle whenever you are given an angle between two equal sides. Now moving on to a right-angled triangle. A right-angled triangle is a triangle with a right angle. Remember, you have your acute angles between 0 and 90 degrees, excluding 90 degrees. You have your right angle, which is 90 degrees, exactly 90 degrees. And then you have your obtuse angles between 90 and 180, excluding 90 and 180. And then you have 180 straight angles. So right-angled triangle, with that being said, is a triangle with a 90 degrees. So when you take a triangle and then you put a 90 degrees, remember 90 degrees is represented this way. So when you take a 90 degrees, which is a right angle, and then put it in a triangle, that triangle is said to be right angled. So the triangle then becomes a right angled triangle because it has a right angle in it. So we already know with the right angle triangle, one angle is 90 degrees for sure. And then we can determine the two unknown angles. Not the same way we did with the isosceles triangle though. So there must be another way of determining these two unknown angles. The nice thing about this type of triangle, you are able to use your Pythagoras theorem. This is the only triangle where you are allowed to use the Pythagoras theorem. This is the only triangle where you are allowed to use trig ratios, your SOHCAHTOA. This is the only triangle where you are allowed to use the half base times height when calculating the area. That's all I wanted to say about the right angle triangle. And then a scalene triangle is a triangle with no equal sides and no equal angles. So a scalene is something that might look like this. So with 3 different sides, you have 3 different angles. Remember, the equilateral triangle had 3 equal sides and 3 equal angles. Isosceles, 2 equal sides, 2 equal angles. So if we have 3 unequal sides, then we'll have 3 unequal angles as well. That's it about the scaling triangles. Okay, now we move on to lines because that's very important as well. Let's consider the straight line here. Let's say this is the straight line A, B, C. I'm sure we know what this angle here is. This angle here is 180 because these are angles on a straight line. So whenever you have a straight line and then you want to determine this angle, what this angle is, you're gonna use that theorem which states that angles on a straight line are supplementary. That is to say, let's say we have something like this. I'm not sure if I've explained this properly, but let's say you have something like this. This is the straight line A, B, C, and you have your 30 degrees here. So if this is 30 degrees, then this one is gonna be 150 degrees. Because these two angles lie on straight line ABC, and angles on a straight line are supplementary, meaning they add up to 180. So angles on a straight line always add up to 108. That's why I'm able to determine the unknown whenever I'm given one angle. Just like here, I was given a 30 degrees and then I had to figure out what the other one was. I just said a 30 degrees plus an unknown equals 108, and then I subtracted a 30 degrees from 108 to get a 150 degrees. Regardless of the number of angles given on the straight line, they always add up to 108. Even if you have 5 angles along the same straight line, those angles add up to 108. For example, let's say we have something like this. Say this is straight line ABC, and then you have your angles along this straight line AB. If this is 10, this is 20, this is 30, this is 15, then this one is unknown. We can easily figure out what this one is by just adding all these angles and then subtract the sum from 180. That is to say, okay, we have 10 degrees plus 20 degrees plus 30 degrees plus 15 degrees, and that is 75 degrees. And then you're going to say 180 minus 75 degrees, and that's your unknown angle, which is 105 degrees. I'm not sure if you understand. Now, let's consider a straight line again, A, B, C. Remember, the angle here we said is 180 angles on a straight line. And that means even the angle here is supposed to be 180 because these are also angles, or this is also an angle along the straight line. Now 180 plus 180, we have 360 degrees. So whenever you have angles around a point, regardless of the number of those angles, they always add up to 360. That's the theorem. For example, let's say you're given something like this, and then you have here an angle of 330 degrees. We know that whenever you add the angles around, say, this point, angles around this point, you're gonna get 360. So the unknown angle here has to be 30 degrees, has to be equals 30 degrees, so that whenever you add 330 and a 30 degrees, you get 360 degrees. That's another important theorem you need to familiarize yourself with. Another important theorem, whenever you're given straight lines, let's say this is a straight line you are told, and this one is a straight line. Then if that's the case, the angle here equals the angle here, vertical opposite angles. The angle here equals the angle here, vertical opposite angles. Remember, these two add up to 180, these two add up to 180, and then these add up to 360. Now let's consider these two lines. Let's say we are told that these two lines are parallel. In Euclidean geometry, this is meaningless until there's a line drawn connecting these two lines. For example, a line going this way. Then we will have three theorems coming out of this diagram. Remember your fan. I'm sure you can see an F being created by these lines. This is F for fun. And then I'm sure you can see U being created by these lines. Although it's the other way around, but it's U. I'm sure you can see N being created by these lines, although it's the other way, but it's N. Now with fun, you have your corresponding angles, your co-interior angles, and your alternating angles. Okay, corresponding angles, remember these are parallel lines. These two are parallel, these two are parallel, and these two are parallel as well. Okay, so these two correspond because they are rather situated the same in relation to the parallel lines. You see, these two angles are both beneath these parallel lines, so they correspond in that manner. So corresponding angles. Corresponding angles, by the way, are equal. And then you have these parallel lines and then these angles inside here. So these two are inside the parallel lines and they are not equal, but they cooperate to give us a sum of 180 degrees. So they are because they cooperate. They are not necessarily equal, but they cooperate to give us a sum of 180 degrees. They are also interior. So those are interior angles. Interior angles. Co for cooperating, and then interior for being interior, inside the parallel lines. I'm not sure if you understand. So we have this one plus this one equals 180. Those are called interior angles. And then you have your alternating angles. This one alternates. So these are alternating angles. Alternating angles are also equal. So we have corresponding angles which are equal. Co-interior angles, they add up to 180. And then alternating angles, they are equal as well. Whenever you have parallel lines, you need to always think of fun. F is for corresponding angles, C is for co-interior angles, N is for alternating angles. Okay, before I move on to the circle geometry or the Euclidean geometry as you know it, I'd like to go back to the triangle theorems. Let's say we have triangle ABC, BC, and we extend a line from C to D such that BCD is a straight line. Then this one is gonna be an exterior angle of our triangle. And the exterior angle of a triangle equals the sum of the opposite angles in that triangle. Let's say this is C1, this is C2. Then C2 equals angle A plus angle B. That's the theorem, exterior angle of a triangle. Exterior angle of a triangle. Make sure you always recall this theorem. So important. Before we get to what exactly this video is about, I just want us to look at this circle and all these details on the circle. Now, this is the circumference. This is what we call the circumference of the circle. That is important to know. Another important thing is the center of the circle, but you need to be told that this is the center. We do not just assume that this is the center. When you read through the statement, you have to be told that this is the center. Then you're going to say this is the center because I'm being told that it is a center. Another thing, a line drawn from center to the circumference. Remember, you now know what the circumference is. So a line drawn from the center to the circumference of the circle is called the radius. The radius. So this is the radius. And then a line drawn from the circumference to the circumference is called a chord. So this is still a chord, but a special type of a chord. This is the chord that passes through the center. So a chord that passes through a center is called a diameter. But any line from the circumference to the circumference of the circle is a chord. But do not call a diameter a chord. Just say it's a diameter. And then a line from outside the circle and then passes through a circle to the other side is called a secant. And then a line that touches a circle at one point is called a tangent. So if it's a straight line outside a circle that touches the circle at one point, it's called a tangent. And then the area here is called a segment. This one is also a segment. Now, with that being said, we can then move on to theorems. One theorem states that a line drawn from center of the circle perpendicular to a chord bisects the chord. So these are keywords, perpendicular and bisects. So a perpendicular is a 90 degrees. I'm sure you can recall that. And then when a line bisects another line, or when the line is bisected, that simply means that the line has been divided into two equal parts. So for example, let's say I have a line AB, 10 meter long, and then this line is bisected. So it means that this line is going to be divided into a 5 meter and a 5 meter. That is what bisect means. So the theorem states that a line drawn from center perpendicular to chord bisects the chord. So let's say we have line AB equals 10. Okay, let me say 20. Let's say we have line AB equals 20 meters. And then OC, O is the center, OC is the line from center to chord AB. And line OC is orientated such that it creates an angle of 90 degrees when it gets to the chord AB. Then the chord AB is going to be divided into two equal parts, namely part AC and part CB. So to bisect is to divide AB such that AC is going to be 10 meters and BC is going to be 10 meters. And the line OC only does that if when it gets to line AB is perpendicular or creates an angle of 90 degrees. Now, there's an application of this theorem. Let's say, for example, we connect a line here. So line OC is extended. Say this is D. And then we extend, we join A, D to create a right-angled triangle ACD. Remember, if this is 90 degrees, then this is 90 degrees, angles on a straight line. Remember, we had, here we have 10 meters, so AC is 10 meters. Let's say we join another line here to create another right-angled triangle OCB. Say this is 15 meters. Okay, and then they want us to calculate the side AB. So this might be the application of this theorem with the lines created here and your triangles. You are able to calculate the unknowns, because remember, you can only be able to calculate side AB by first determining what side DC is, and then use your Pythagoras theorem, since this triangle is a right-angled triangle. So how can we determine what side DC is? Remember, a line from center to the circumference is the radius. So OB is the radius. Then OD is also a radius. So we have 15 meters for OD. So we can say OD is 15 meters. Reason is radi, the plural form of radius. Now, I'm not sure of the pronunciation though, if it's radi or what. So now we have 15 meters here. We only left with this part to determine this one, so that we'll have the whole distance CD. How do you determine this unknown? Remember, also BC is 10 meters. Now you can determine OC using this triangle and the Pythagoras theorem. You solve for y. R squared equals x squared plus y squared, and then you'll have your OC, and then you have OC and OD equals CD, and then you calculate the R for this triangle here. Okay, this was just an introduction to the application of the theorem. Let us move on to the next theorem, which states that angle at the center is 2 times angle at the circumference. Now, you know what the circumference is already. You know what the center is. Let's say when you read through the statement, you were told that O is the center. For this theorem to exist, firstly, A has to touch the circumference, B has to touch the circumference, and C has to touch the circumference also. O has to be a center for this theorem to exist. You need to be careful about such. Now, the angle at the center here is angle BOC. This angle here is the angle at the center. And this is the one that is 2 times the angle at the circumference. As you can see, this one looks smaller. Now, if this is 2x, then this is x. If this is 100 degrees, then this is 100 degrees times 2, and that's 200 degrees. But you need to be very careful, and you need to be able to see whenever you are given different forms of this theorem, because this theorem can be represented in 4 different ways. One is this one, and then I'm just going to show you another ways in which this theorem can be represented. First, you need to understand what this theorem states, and then the conditions for this theorem to exist, and then the different forms of representation. Now let's have a look at the diagram here. This is the theorem I've just introduced. Now, let's say these 2 points are fixed here, and then we move point A. So if we move point A to here, then the diagram will be looking like this. I'm not sure if you get what I'm trying to explain. When we further move point A, say to this point, then the diagram will be looking like this. When we further move it, say we move it here, the diagram will be looking like this. I'm not sure if now if you notice now that some part of line AB is now on top of line OB, so that the diagram now looks like this one over here. So that's another way they can represent the theorem angle at the center is 2 times angle at the circumference. It can be represented this way. And what I'm noticing right now is that AB is a diameter. So whenever you are given a diameter, you need to also take into account that this theorem might exist. The angle at the center is 2 times angle at the circumference. If we further move point A such that it's now here, then the diagram will be looking like this one over here. Even here, the angle at the center is 2 times angle at the circumference. Another representation is this one. The last representation is this one. You need to be careful with this one. The angle at the center is no longer this one, but this one over here. So this is the angle at the center, and then this is the angle at the circumference. So whenever you are given this one over here, you can always subtract it from 360 to get this one. Remember, angles around a point sum up to 360. So for you to get this one, given this one, you just subtract this one from 306, and then you have your angle at the center, and then this one divided by 2, you're gonna get the angle at the circumference, because the angle at the center is 2 times the angle at the circumference. Moving on to the next theorem, the angle subtended by the diameter, or diameter subtends a right angle. A right angle is 90 degrees, remember. I would like to first point out the conditions for this theorem to exist. Firstly, you need to have a diameter, and the diameter has to subtend an angle not just anywhere but on the circumference of the circle. So for example, let's say you have this angle over here. Yes, this angle is subtended by the diameter AB, if AB is a diameter. So you need to make sure that AB is a diameter, but we do not assume. You have to be told that AB is a diameter. Then any angle subtended by diameter, you have to check whether it is subtended at the circumference or not at the circumference. Because the angle over here, yes, it's subtended by line AB, the diameter, but not at the circumference. So here the theorem does not exist. So whenever the diameter subtends an angle at the circumference, just like in this case, then the angle is a right angle or a 90 degrees. It doesn't matter really how many angles are subtended by the diameter, for as long as those angles are subtended at the circumference, then those angles are going to be 90 degrees. Even this one is a 90 degrees because it is subtended by the diameter at the circumference of the circle. Even with the case of a semicircle or half circle, you'll still have the angle subtended by the diameter. So if this is the semicircle, there's no need for them to tell you that this is the diameter. This one over here is a diameter. Because a semicircle is a result of a circle being cut into 2 equal parts. And if that is the case, then the angle subtended by this line, the diameter, at the circumference is still going to be a 90 degrees. I think that's it with the angle subtended by the diameter. So you need to be careful with the diameter. Whenever you are given a diameter, recall that the angle subtended by the diameter at the circumference is a right angle or is a 90 degrees. So with this one, we have a right angled triangle for in case you are given sides, because sometimes they give you sides and then you have to solve the unknown side. And then let's move on to the next theorem, angles in the same segment. With this one, you'll have to have a bow tie-like figure or a zigzag. And the conditions for this one to exist, A has to be at the circumference of the circle, B has to be at the circumference, C has to be at the circumference, and D has to be at the circumference. If one of these is not at the circumference, then the theorem does not exist. Now, with this one, you'll have angle A equals angle B. Reason, angles in the same segment. You'll have angle C equals angle D. Reason, angles in the same segment. They sometimes give you a diagram where you'll have two of the bow ties. So with two bow ties, you'll have something of this nature. Let's say we extend a line joining A and B, and then a line joining C and D. Then you'll have another zigzag, this zigzag or this bow tie with this angle equals this angle, this angle. Okay, let me use another color. This angle equals this angle, and this angle equals this angle, this one equals this one. Whenever you are given something like this, just know that you have two of these. Okay, another theorem states that equal chords subtend equal angles at the circumference and at the center. If chord AB is equal to chord DE, and chord AB subtends an angle at the circumference just like it did with angle C, and chord DE subtends an angle at the circumference just like it did with angle A, then angle A and angle C are going to be equal angles. The reason, equal chords, equal angle. This is for when chords subtend angles at the circumference. And then with center, you need to be told that this one is a center, always the center, and then you can conclude that if AB is equals CD, remember these are chords, the angles subtended by these two chords at the center are going to be equal. Equal chords, equal angles, but this time at the center. So these two chords subtend angles at the center of the circle. So they have to be equal. That's the theorem. So whenever you have equal lines, think of this theorem, especially equal lines in different triangles. Another theorem states that the opposite angles of a cyclic quadrilateral are supplementary. So a quadrilateral is any four-sided figure, like a square. A square is a quadrilateral. A rectangle is a quadrilateral because it has four sides. A trapezium is a quadrilateral. So for a quadrilateral to be a cyclic quadrilateral, or the quadrilateral of the cycle, it has to fit perfectly on the cycle. Just like this, the quadrilateral ABCD. The quadrilateral ABCD fits perfectly in this circle. That is to say, a vertex A is at the circumference of the circle, B is at the circumference, C is at the circumference, D is at the circumference. That makes this figure a cyclic quad, or a quad of a circle. And if that's the case, then opposite angles are supplementary. They are not necessarily equal, but when you add them, you get a 180 degrees opposite angles of a cyclic quad. So when you add them, you're gonna get 180 degrees. That's the theorem, opposite angles of the cyclic quad. No matter how small the cyclic quad looks, no matter how funny the cyclic quad looks, as long as four corners of the cyclic quad are at the circumference, then that's the cyclic quad, and the theorem therefore exists. So whenever you extend a line from a cyclic quad, for example here we extended line DE such that CDE is a straight line, then the angle here is the exterior angle of a cyclic quad because it's outside the cyclic quad. An exterior angle of a cyclic quad equals the interior opposite angle. That's the theorem. The exterior angle of a cyclic quad equals the interior opposite. Even if we extended, let's say we extended a line this way, then this angle would have been the same as this one over here. If we extended this way, say we extended this way, then this angle would have been the same as this angle over here. That's the exterior angle of a cyclic quad. Even if we were to extend this way, this angle over here would have been the same as this angle over here. And it makes sense because these two are actually equal angles. Reason is vertical opposite angles, if you remember when I was still discussing lines with you. Let us now have a look at the tan-chord theorem, or tangent chord theorem. I'm sure you already know what a tangent is and what a chord is. In this diagram, we have chord AB, chord BC, and chord AC. The tangent is line DCE. An angle between a tangent and a chord is called a tan-chord angle. This angle over here, according to the tan-chord theorem, is going to be equal to the angle subtended by this chord. And the angle subtended by this chord is angle B. Another tan-chord angle, remember this is the tangent and this is chord BC. An angle between the tangent and the chord is the tan-chord angle. And this angle over here is going to be equal to the angle subtended by this chord, chord BC. And the angle subtended by chord BC is angle A. So according to tan-chord theorem, angle C in triangle ACE equals angle B in triangle ABC. And angle C in triangle BCD equals angle A in triangle ABC. That's your tan-chord theorem. Another tangent theorem is tangent is perpendicular to radius. So let's say O is the center. If O is the center, then OB is the radius. And suppose we were told that ABC is a tangent, because we do not assume, we have to be told that ABC is a tangent, then that's when we can be sure ABC is a tangent. And if that's the case, then the radius is going to be perpendicular to the tangent, or tangent is going to be perpendicular to the radius. Remember, perpendicular is 90 degrees. So the angle here is going to be a 90 degrees. Now, suppose the line OB was extended such that we now have the diameter instead. Then the tangent would be perpendicular to the diameter in that case. So these are two almost similar theorems. The first one, it's a radius. The second one, it's a diameter. So tangent is perpendicular to both the radius and the diameter. Okay, here's another one with two tangents. So this one states that whenever you have two tangents drawn from the same point outside the circle to the circle, then those tangents are equal in length. That is to say, side AB equals AC. And this thing is not that useful until there's a line drawn connecting point B and point C. So when there's a line connecting point B and point C, then you'll have an isosceles triangle. Because if you look at triangle ABC, we have two equal sides, and the angles opposite equal sides are equal. That's the isosceles triangle. That's the application of this theorem. I know you guys find it hard to master this topic. One of the reasons being you are unable to recall all the theorems. Now, let me introduce you to Dr. Cape Town. Dr. Cape Town is the one that is going to help you recall the theorem. D is for diameter. And the diameter theorems are your angle subtended by diameter. Remember that 90 degrees angle subtended by diameter at the circumference. Your diameter is perpendicular to radius, remember? And that special case of angle at the center is 2 times angle at the circumference. Remember that special case where you have something of this nature. And then this is your angle at the center, 2 times angle at the circumference. Remember, this will be your diameter. So whenever you see a diameter, think of this theorem as well. And then R is for radii, the plural form of radius. Now, with this one, you have your radius is perpendicular to tangent. Okay, C is for chords. Your opposite angles of a cyclic quad, remember, all these are chords. Your exterior angle of a cyclic quad, they are chords. Your angles in the same segment, these are chords. Your equal chords, equal angles, those are chords. And then with P, you have parallel lines. Remember, with parallel lines, you have fan. F is for corresponding angles. Remember, corresponding angles are equal. You have co-interior angles. These two are supplementary. Then N is alternating angles. These two are equal. Then T is for tangents. Your tan chord theorem, your tangents drawn from the same point. So with the help of Dr. Cape Town, you are able to recall all the theorems. But there's another strategy I'll introduce you to when I'm solving problems from past papers in the next video. So be sure to subscribe, turn on the notification bell so that whenever I post a new video, you get notified. Like the video, comment and share.